Hi guys, this is our product. This is an SDN based hardware accelerated firewall, and these are my teammates. I'm Abhishek, and my teammates are Arun, Joseph, Vasantam, and Santosh. So, what is the primary motivation for our product? Is that on Jan 25th, 5:30 a.m., there was a computer worm which got released into the web, and it's called Sapphire. Uh, the Sapphire spread to 5 continents within 30 minutes and affected more than 75,000 hosts. One unique feature of Sapphire was that it could spread at line speed. Back then, the internet speed was around 100 megabits per second, and it could affect roughly around 30,000 hosts in one scan. That is, it could affect 30,000 hosts per second. So this resulted in huge losses up to 1.2 billion. Now our product mitigates the effects of these worms which can spread at line speed, and we have implemented a multi-core, multi-threaded processor with hardware accelerators that can be remotely controlled by an SDN controller and updated by an SDN controller. So this demo shows the basic experiment setup and the basic functionality of our product.
Hi again, this is Yusuf. I'm gonna go over the gist of our product. So you can see NetFPGA is sitting right in the middle with four nodes. We have a control node, node 1 and node 2 and node 3. So let's assume that we have a normal packet coming in from node 1. It will go to our router and the router will process the packet and send over to node 3. This is a normal packet, a clean packet. And let's say we have another packet with a pattern that we want to match. And in the net FPGA design, we have hardware accelerated design where we have two lists. One is a good list, allow list, and the other one is a deny list. And let's assume the last packet that you saw is within the allow list, and this is will be sent to a node 2 still because this node 2 is in the allow list. Let's assume the next packet comes in with a pattern that we want to match, and the source address of the node 1 is actually in the drop list, which is a deny list, and this packet will be dropped in the net FPGA itself. It won't be rerouted to the destination. And let's assume another packet with a pattern coming from node 1, and let's assume right now node 1 is unknown to the net FPGA. It will reroute this packet to a control node up there, and then the control node will decide whether node 1 is to be put in a good list or a bad list. And then an instruction packet is generated in the control node and is going to be sent to NetFPGA to update our hardware accelerator to put node 1 in either good list or bad list.
So this is the basic setup, experimental setup of our product, where the SDN based firewall, the entire setup is sitting on a net FPGA, and this is a net FPGA 1G, and the experiment is set up such that four nodes N1, N0, N3, and N2 are connected to the net FPGA via the net FPGA ports, and each connection is 1 gigabits. The maximum bandwidth through each port is 1 gigabits. Now in this experiment setup, we have made N3 as the control node, which acts as a controller and pushes in the updates to the data plane, which is the NF router. The SDN architecture in our design is that we have a control, we have separated the control plane, that is the N3, from the data plane, which is the router.
I'm gonna run a test script right now to program the net FPGA. So the net FPGA right now is programming two software for thread 1 and thread 2. They are both going into core 1 and core 2 of our processor. So just to go quickly on what the thread 1 is doing, the thread 1 will come in and then it will check on the action of the action table based on our hardware accelerator. If the action table say this is drop, then it will drop the packet, and by doing this it will drop the packet. And if the action is saying reroute, then this is doing the rerouting to our control node, and all the task is done here. For the thread 2, what we have is we have another action where if only when we are doing reroute, we are actually going to another hardware accelerator of our design, where we will update the MAC address, and also we will update the IP of the destination, and we will then update the checksum into the packet itself, and then finish the thread. So thread 1 and thread 2 will actually talk to each one of our hardware accelerator per each core, and then do the decision whether to drop the packet, to allow the packet, or to reroute the packet to our control node. Okay, so now the programming is done. So we should have the software running on our CPU. So the top two terminals that you see at the top here are TCP dump, just to show you the received packets. On the left here is actually from node 3, which is our control node, and on the right here is the node 0, which is one of the nodes that we are sending packets to. So if you remember, node 3 is the control node. So any ping that we are sending is actually sending from node 2 going through node 0. So any packet that will go through the network will actually go through our router, which is in the middle, NetFPGA, and then will go to node 0. So the first thing to do is for me to ping from node 2 to node 0. The expectation here is you should get a reply. So from node 2 and node 0, and you are seeing a reply of 0.177 millisecond. So this is okay, as expected. And now we're going to step 2. We are trying to ping from node 2 to node 0 by sending a bad pattern. For the purpose of our demo, we actually define our bad pattern as ABCDEFGH as ASCII. So we are sending it through ping 41, 42, 43 until 48 as the representation for 8. So we're pinging the bad packet, and the expectation here is node 2 should not be getting a reply, and node 3 at the top here should be getting the packet, because node 3 is the control node. So as you can see, node 3 is getting a rerouted packet here. And also you notice that node 2 is not getting any reply. That's why it's stuck there. In real life, we would have a software in node 3 to do decision making, thinking whether it's node 2 should be allowed or should be put in the bad list. Let's assume that node 3, which is the control, has decided that node 2 and node 0 should be put in a good list. So we are sending a ping packet. These are instruction packets to the router, so that node 0 and node 2 will be put in a good list. So from node 3, which is the control node, we are sending instruction packet. And this is okay. Another instruction packet for node 0. So right now, the expectation is node 0 and node 2 should be in the good list. So if we go back to node 2, if we want to send bad packet, it should be going through to node 0 at the top on the right here, and node 0 should be able to reply to node 2 back. And as you can see, now you are getting the ping from node 0 as a reply. So you can see ICMP echo reply here. So this is working as expected. Let's go to step number 5. Let's assume right now the control node is gonna make node 2 as a bad node. So we'll go to the control node, and then we'll send an instruction packet that says node 2 now is a bad node. after the update, the node 2 will be in the bad list, and then we'll move to step number 6, and this ping to node 0 should not be going through anymore. And as you can see, the packet has been dropped and not even rerouted to control node because node 2 now is in the bad list. So you can see at the top left, node 0, there's no packet, and node also on node 0, there's no packet.
Hi guys, I'm Santosh. I'm gonna compare the performance of our hardware with the software, and I'm gonna compare with the paper. And this is the paper which has already been implemented. They have implemented a open flow switch on the Neft FPGA. Okay, what they have done is they have used a UDP package to update the net FPGA, and since it's like a firmware where you just use the UDP package to update the net FPGA with new entries. Okay, and here is the table. As you can see, for packet size 64, which is a ping packet, they are able to achieve 61,000 flows per second, which means they are able to update 61,000 new entries per second. And if you look at our processor, and each ping packet takes 0.1 microseconds, and that means in each second we're gonna receive 10 power 7 10% packets. That means since each packet can update new one entry, the number of updates per second is 10 power 7. And then if you see the comparison, it's 10 power 7, that is 100 meg over 61k, which is 163.93x, which is pretty big when you consider that the software, the comparison is with the firmware. Okay, when you consider a packet size which is of 512 bytes, the improvement would be 35.2, which is better, may not be as good as 163.93. And this is with the firmware, and you can think, if you compare with the software, how much the performance would be. Okay, and thank you guys, thank you for watching this video.